You've probably heard of LEDs before, light-emitting diodes. But you might wonder, what exactly is a diode anyway? Well, a diode is an electronic component that lets electricity flow in one direction. It's a lot like a valve that prevents water from flowing the wrong way, but lets it pass in the forward direction. Some are designed for use with low electrical current. These are often called signal diodes. Others, usually much larger, are designed for use with higher current. These are usually referred to as rectifier diodes. A diode's ability to turn AC or alternating current into DC, direct current, is referred to as rectification. Now, a diode isn't perfect. It can only withstand electricity flowing in reverse up to a certain amount of voltage. This is called the breakdown voltage. Once this amount is exceeded, the diode's valve is essentially broken and current will flow in reverse. In 1874, German physicist Ferdinand Braun was studying the electrical properties of crystals when he discovered what could probably be considered the very first diode. While probing the surface of a piece of iron sulfide with a thin metal wire, Braun found that electricity would move in only one direction through the connection he'd made. He went on to demonstrate the effect to the public, but few at the time understood the potential there. Indian physicist Jagadish Chandra Bose was using a similar setup with galena crystals. He used it to detect electromagnetic waves. In 1901, he patented it as a method for detecting radio signals. Braun's discovery had found a practical use. As their popularity grew, these crystal detectors, basically do-it-yourself diodes, became further developed by others. An electrical engineer from Portland, Maine, named Greenleaf W. Pickard, began experimenting with thousands of different minerals for use as rectifying diodes. He finally settled on silicon as the best choice and patented his silicon detector in 1906. Pickard would go on to start his own company, selling more permanent versions of the crystal detectors. At the basic level, these crystal detectors are really similar to point contact diodes. Point contacts are still in use today for high-speed applications, but most of the diodes you'll run into will use a different technology called a PN junction. In 1939, Russell Schumacher Ohl discovered that by adding small amounts of specific impurities to a semiconductor crystal, one could control how well they conduct electricity. This process, known as doping, can be used to give a semiconductor either a positive p-type or negative n-type charge, depending on which impurities are added to them. When these two types are brought together, a PN junction is formed, which will conduct electricity only in one direction.
Some of the different types are light-emitting diode LED. It is one of the most popular type of diodes, and when this diode permits the transfer of electric current between the electrodes, light is produced. Schottky diodes. These diodes feature lower forward voltage drop as compared to the ordinary silicon PN junction diodes. The voltage drop may be somewhere between 0.15 and 0.4 volts at low currents, as compared to the 0.6 volts for a silicon diode. Schottky diodes are used in RF applications, rectifier applications and clamping diodes. Zener diode. This type of diode provides a stable reference voltage, thus is a very useful type and is used in vast quantities. The diode runs in reverse bias, and breaks down on the arrival of a certain voltage. A stable voltage is produced if the current through the resistor is limited. In power supplies, these diodes are widely used to provide a reference voltage, rectifier diode. These diodes are used to rectify alternating power inputs in power supplies. They can rectify current levels that range from an amp upwards. If low voltage drops are required, then Schottky diodes can be used. However, generally these diodes are PN junction diodes, silicon-controlled rectifier. As the name implies, this diode can be controlled or triggered to the ON condition due to the application of small voltage. They belong to the family of thyristors and is used in various fields of DC motor control, generator field regulation, lighting system control and variable frequency drive. This is three-terminal device with anode, cathode and third controlled lead or gate.
Here's a quick illustration how you can test a diode with an analog meter. I've got it on R times 1. And if we read this way, see it doesn't read. If you read this way, it reads. So, as you can see, this line is on the negative lead, positive lead. It can flow through that way, but not this way. Now, if you have a digital meter, it doesn't work nearly as good. I think that analog meters must push a little more current through, and it really works well. But digital meters, you're going to see it read both ways, and you just kind of have to make a decision as to which way it reads more or less.
It took decades to perfect the process of producing silicon with a perfect monocrystalline structure. They begin with raw polysilicon, or poly, and heat it to over 2,500 degrees Fahrenheit inside a special sealed furnace, which has been purged with argon gas to eliminate any air. The resulting lake of molten silicon is then spun in a crucible, and a silicon seed crystal, roughly the size and shape of a pencil, is lowered into it while spinning in the opposite direction. As the molten polysilicon is allowed to cool, the seed crystal is slowly withdrawn at around 1.5 millimeters a minute. The result is a single silicon crystal weighing around 440 pounds and with a diameter of around 200 millimeters. The crystal is so strong its entire weight can be supported by a single thread just 3 millimeters across. But it is brittle, and it must now be cut down to size without shattering. After testing with chemicals and X-rays to check its purity and molecular orientation, it's fed to a silicon salami slicer. This 10-ton wire saw uses a fast-moving web of ultra-thin wire to produce wafers of silicon that are just 2/3 of a millimeter thick and 99.999% pure. Once cut, there are microscopic marks left on the wafer's surface, so it's time for a buffing using a process called lapping. After a twirl in this high-powered polisher, they are still not smooth enough. So they're given yet another buff using a chemical process. The result is wafers of silicon with a surface roughness of less than 1/millionth of a millimeter. Buffed to a sheen, they're finally ready for etching with the circuit designed.